All right, so we left off the previous video here talking about how we take multiple samples and we get different statistics from them depending on where the sample comes from. So the big question becomes, how can X bar be an accurate estimate of mu? Different random samples produce different X bars, different standard deviations, different ranges, all these different statistical values. How can that be good for the population? How can we really know that that is representative of our population? So that's what we're going to get into. And what we're going to do is we're going to do an activity. It's a modified activity. We're not going to do this reaching for chips thing. It refers to page 418 in the textbook. But we are going to take a sample of 20 and we're going to record the proportion of Reese's Pieces. So here's what we're going to do. There's a website, it has a nice applet on it. The website's here if you want to go there. We're going to deal with Reese's Pieces. This is a vending machine right here. It has 50% orange Reese's Pieces. That's what this first 0.5 is. And we're going to collect samples of 20 pieces of candy. And so I'm going to draw the sample, and here come my Reese's Pieces. They're falling out. It's going to keep track of how many Reese's Pieces I get. So I got 10. What I want to look at is the proportion of oranges. So now you can see my dot plot down here above the 0.5. I have a dot. And I can do that again. And so another random sample. This time I got 0.45 as my sample proportion, p hat. And there it is on my dot plot. And I can continue doing this. Here's another sample. I'm going to turn off my animation. And I'm going to collect multiple samples here. And notice how they're spread out. They're not all the same time after time. I've got a range from 0.3 of my proportion to 0.8. Now, let's see what happens if, instead of just sampling one, let's sample 100 times. Boom. 212. And look at what happens as we sample more and more and more. And the thing I want you to notice is this looks remarkably like a normal distribution. And that's what we're going to discover, and that's what we're going to be dealing with a lot, is we're going to be dealing with sampling these means enough times that we can have an approximately normal distribution. And to me, that's really cool and really powerful, and we're going to start looking at how to do that. So, in this activity, there are many possible simple random samples of size 20 from a population of size 200. So regardless of what our population is, if we are going to have a sampling distribution, we are taking every possible sample that we can of the same size. So if I go back to my Reese's Pieces, if I collected every single possible group of 20 that there is, then it's a true sampling distribution. Now, it's difficult to take all possible samples of size n. It's usually infeasible to do that. So what we do is we can use simulation to imitate the process of taking many, many samples. We're never going to get them all. We're never going to have a true sampling distribution, but we can get close to it. So we deal with probability theory, normal distributions, that sort of thing, and we can obtain sampling distributions without simulation. We're not going to get into that right now. So, there's three distinct distributions involved in what we just did. There's a population distribution, there's a distribution of sample data, and there's the sampling distribution. And this next graphic illustrates that. So if I was just dealing with, I guess in my case, I would be looking at, I'm going to change this slide a little bit for our Reese's Pieces. So I'm going to deal with orange and not orange. And if I look at each one of my samples, we'll get a distribution of orange and not orange, orange and not orange, and so on. And we get a sample proportion from that. So 8 out of 20, 0.4, 11 out of 20, 0.55. 13 out of 20.65. So each one of these is an individual sample. And we're sampling from this total distribution, this population distribution, where half of the candies are orange and half are not orange. And then we record these samples, these sample proportions in a dot plot, and if we do enough of them, we start to see this sampling distribution take form, and it ends up being very close to normal. Okay, so how trustworthy is a statistic as an estimate of the parameter? How trustworthy is x bar if we're really looking at mu? To get a complete answer, we need to look at center, spread, and shape, our socks. So for center, we think about biased and unbiased estimators. In the chips example, or in our Reese's Pieces example, we collected many samples of size 20 and calculated the sample proportion of orange Reese's Pieces. How well does the sample proportion estimate the true proportion of orange Reese's Pieces? Well, if I go back to my simulation, I'd say it does a really good job of estimating 0.5. So this is unbiased, we would say. If we took all possible samples of size 20, we'd get a mean, an average value of these proportions of exactly 0.5. So a statistic used to estimate a parameter is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. So in my distribution here, remember the mean of a normal distribution is right in the middle. My normal distribution is centered effectively at 0.5. This sample proportion, this distribution of them is an unbiased estimate. To get a trustworthy estimate, start by using a statistic that's unbiased. We don't want to use a statistic that has bias. It's not going to give us a good estimate. A lot of times, though, unbiased estimates don't guarantee that we'll be close to the actual parameter. And something to know is we can get that better by using a larger sample size. Notice for sample size of 100, we get this distribution. For a sample size of 1,000, we get this distribution. Much smaller, much more likely to produce an estimate close to the true value. Note there's much less variability in this distribution than this one. So we want low bias and large number of trials. Less bias, more trials means better estimate. And that should make sense, guys. We've talked about these sorts of things before. So the variability of a statistic is described by the spread of its sampling distribution. So how much variability does this proportion have? Well, it depends on how spread out our sampling distribution is. The spread is determined primarily by the size of the random sample. Again, more samples leads to less variability. The spread of the sampling distribution does not depend on the population. And there's a caveat on that. As long as the population is at least 10 times larger than the sample. So we're dealing with that 1/10 of the population. We saw that in the previous chapter. So let's talk about bias and variability. We can envision this with archery. Here at WPS we do have an archery team. So here's our target. If we shoot a bunch of arrows into the target and they all land here, that's like high bias, low variability. If our arrows go all over the place, that's not biased, but there's high variability. Bias means that our aim is off and we consistently miss the bullseye in the same direction. So these two, there is high bias. We're always up and to the right. High variability means that the shots are more scattered. So these two have low variability. Our arrows are all in the same spot. One has high bias, the other one does not. This is ideal. We're hitting what we're aiming for on a consistent basis. Given a choice of statistics to estimate an unknown parameter, choose one that has no bias, or at least low bias, and as little variability as possible. Sampling distributions can take on many shapes. The same statistics can have sampling distributions with different shapes depending on the population distribution and sample size. Be sure to consider the shape of the sampling distribution before doing inference. So these are some different things that we can measure, that we can sample: max, min, the mean standard deviation, twice the mean. We'll look at different measurements, different statistics that we can take. The blue line on these represents the true number of tanks. These numbers represent the number of tanks. If you want to read about the German tank problem, it's in the textbook that I do use. Notice the different shape. Which one, and I don't care if you understand the tank problem or not, which statistic gives us the best estimate? Take a look at them. We want one that has low bias and low variability. So we want one that the mean is centered at the true mean, and we want one that's not as spread out as possible. And I would say that this top one is doing a pretty good job of not being biased. Its high point, its line of symmetry, if you will, is right at the mean. The other ones don't really have that. And I would say it has the least amount of variability. Also, considering that this last one, although there's not as much variability, it looks like it's quite biased. There's a lot of things that are consistently high. So there we have it. That's looking at which one might be best, which one is not as good. Here's a summary of this section. Take a look at them. And in the next section, we'll learn how to describe and use the sampling distribution of sample proportions. And that, my friends, is exciting stuff.